Don Machholz, and you are listening to Looking Up with Don. This is the Looking Up with Don podcast, episode number 22 for the week of June 3rd, 2020. The related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com. 2 H's. What's up in the sky this week? As our week begins on Wednesday, June 3rd, we have a bright moon on our evening sky. The moon will be full on June 5th, 19 hours Universal Time. And by the end of the week, June 9th, the moon will be bright in our morning sky. Photographing a full or near full moon rising can produce some fine results, and this is the week to do it. Pursuant to the full moon is that we will have a minor lunar eclipse on June 5th. This is known as a penumbral lunar eclipse, and is when the moon passes through the outer shadow of the Earth. At no time, as seen from the moon, will the sun completely be hidden by the Earth, so the dark shading on the moon will be minor. Unlike a solar eclipse, which can be seen from only a narrow strip across the Earth, with a lunar eclipse, everyone who can see the moon can see the eclipse. That means half the world. With the sun far north of the equator as we near summer, the full moon is just the opposite, just as far south of the equator. So, this eclipse will be visible from southern Europe, most of Africa, that is Eastern Africa, Australia, and Antarctica. The southern part of the moon will be covered by the outer shadow of the Earth. It's not very dazzling, but it is a subtle shading. Sometimes with this type of an eclipse, the astronomers are the only ones who notice it. First Venus, now Mercury, has left the evening stage. I've been impressed by photos posted on Twitter of Venus within just a few degrees of the sun as it prepares to pass just north of the sun on June 3rd. After this point, it will be in the morning sky. Now, this is an exceedingly difficult photograph to accomplish, and it takes the chance of getting too much sun into the telescope and burning something, like the inside of the telescope tube. It's hard to get a good contrast, too, when pointed near the sun, but we have imagers out there doing that. If you stay up past midnight, you can see Jupiter and Saturn in your southeastern sky. Yes, the moon is bright, but get some good views of these planets this week. The moon will be passing south of Jupiter and Saturn on June 8th. I had a 3-day stay in the hospital again, but I'm back home and doing much better. It wasn't the virus, but bronchitis. At the VA hospital in Las Vegas, I was inspected, protected, disinfected, dissected, subjected, injected, directed, connected, respected, and corrected. Will you be able to see the International Space Station this week? If you live north of 45 degrees, you'll not see it at all. But those between about 28 and 45 degrees north will have it in your evening sky for the first few days of the week, then nothing. Chicago, Turkey, Japan, get out there soon. From 17 degrees through 28 degrees north, you can find it in our evening sky the whole week, sometimes twice per week. Florida, Egypt, Iran, you're in luck. Florida, you put 2 of those guys up there, get out there and wave to them. Between about 17 degrees north to the equator, it makes an appearance only late in the week, and those will be evening passes. If you live between the equator and minus 20 degrees, there are no passes this week. Further south, it will be visible in the morning sky later in the week, with New Zealand at minus 44 degrees, seeing it every morning, sometimes twice per morning. To determine where it will be in your sky, you can go to the website heavens-above.com and enter your location, then click on ISS. Now let's talk about comets. A short recent history. In February and March, we were talking about Comet 2019 Y4 Atlas, perhaps becoming a very bright comet in our pre-dawn and post-dusk skies in late May. But by the third week of March, Comet Atlas stopped brightening and started dimming. Everyone said, well, that's okay. We lost Comet Atlas, but we now have the newly discovered Comet 2020 F8 Swan, and it is doing well. In the second week of April, the week it was discovered, Comet Swan began to accelerate in brightness, showing fine form against the dark sky of the Southern Hemisphere, only to stall 3 weeks later, never realizing its full potential. Wait, full potential? Maybe it did live up to its full potential. Every comet is what it is, and every comet has an unknown potential. Meanwhile, Comet 2017 T2 Pan-STARRS has performed well. We've been watching it since early this year, and it has hung out at magnitude 8 to 9 for the whole time. It is not a great comet, but it did put on a consistent display. So what makes a great comet? I'm not talking here about interesting comets. There are some strange comets that deserve continuous study, and they often do not hold the public's attention. Generally, the comets that are remembered are the bright ones, and they must appear bright against the background sky. A comet that is bright against the dark sky must really move up a few notches in brightness if it moves into the twilight sky. The great comets must also show a tail or two. I mean, what is a comet without a tail? Although every comet is different. This is the basic understanding of the makeup of a comet. A comet has been described as a dirty snowball, and this model seems to hold up for most of them. But caution, some snow is dry, some snow is wet, some snow is dusty, some is not. As for snowballs, some are densely packed, some are loosely packed, some are round, and some are odd-shaped. And most important of all, some are large and some are small. This dirty snowball is known as the nucleus. That is the center of the comet, and that's where everything occurs. That drives the performance of the comet. Only when it is far from the sun can the nucleus be seen, and then it's very tiny, often between 1 and 6 miles across. So through even the most powerful telescopes, they look like a star. And they reflect very little light. These are dirty snowballs, as dark as coal or blacktop material. The brightness of the nucleus can be observed, and if we make the correct assumption as to what percentage of light it reflects, this may give us a rough estimate of how large the nucleus is. Sometimes astronomers can pick up the rotational period of the nucleus. That can tell us something. By rotation, I mean how fast the comet spins, not how fast it's traveling through space. Spin rates are generally between 4 hours and 30 hours for one rotation, but not much else can be derived from observations at this early time. By the time most comets are discovered, it's too late to image the nucleus directly. That's because, as the comet nears the sun, the material on its surface and even perhaps some under the surface sublimes. That is, it transfers from a solid ice to a gas, and this material floats or sometimes shoots from the nucleus to form a cloud around the nucleus. This is the coma, also known as the head of the comet. Now covered in cloud, the nucleus is no longer directly visible, and this is where all the action takes place. If waves of material are thrown off as the comet nucleus rotates, we may still pick up the rotational period and maybe even the spin axis, that is, which way the north and south poles of the comet are facing. When a new comet is first discovered, and the coma has already started to form, we have no images or measurements of the nucleus, so we move to the next level of comet evaluation. Within a few days of discovery, we can begin to put the picture together. This is because the orbit is determined by watching the comet's changing positions. So using that orbital calculation, we figure out how far the comet is from both the Earth and the Sun. We make an important calculation based upon three factors: the brightness of the comet as seen from Earth, the distance from the Earth, and the distance from the Sun. From this data, astronomers determine the comet's absolute magnitude. That is, how bright it would be if it were to be placed 1 astronomical unit from both the Earth and the Sun. An astronomical unit is a distance from the Earth to the Sun, about 92 million miles. The absolute magnitude is particularly important in understanding the comet, and it can change during the comet's visit. At this stage, we closely monitor the comet's brightness and appearance. That tells us something about the new comet. As a comet gets closer to the Earth, it will brighten to the inverse square, meaning if it halves its distance to us, it will become 4 times brighter. But a word of caution, as it gets really close to us, and most of them do not, but if it gets really close, like 20 or 30 million miles, then the coma, the head of the comet, gets so large that the light is spread out over a large area and it can become even more difficult to see. It can still be bright, but not impressive. Comet Iris-Araki-Alcock in 1983 demonstrated that, as have other comets. How the comet behaves as it approaches the Sun tells us a lot. This, plus the absolute magnitude, are the two main factors used to determine how bright a comet will get. Over the weeks, the magnitude, that is, the brightness estimates, are made of the comet and fed into the computer. A typical comet will brighten as it approaches the Sun, something like this. If it halves its distance to the Sun, say from 2.0 to 1.0 astronomical units, it may brighten by a factor of 16. This is the tricky part. Some do, most don't. Here's where they do whatever they want. This number often changes as a comet moves closer to the Sun, resulting in brightening fluctuations. So we have 4 factors of continuously updated information as a comet heads toward the Sun. The first 2 are unpredictable. The first is absolute magnitude, which is usually between 5 and 12. Smaller numbers are brighter. And the brightness slope, that is how rapidly it brightens as it nears the Sun. The final 2 factors are known by this time, and they will not change significantly. They are, number 3, the distance of the comet from the Sun now and in the future, And number 4, the distance from the comet to the Earth, now and into the future. From what the comet is doing now, we guess what it will do in the future. So, Comet Kohoutek, discovered in 1973 while still quite far from the Sun. It was very bright for its far distance, and this comet was once promoted as the Comet of the Century. It did do well, but not nearly as well as expected, and became a comet flop. The reason for the high expectations is that this comet was new to the inner solar system, and early on, when we first began observing it, it was burning off a lot of extra volatile gases. So in the early months, it looked bright with more to come. But this left it nearly out of gas as it reached the inner solar system. No one knew at the time that a new comet like this would have excess gases to blow off far from the Sun. This taught astronomers a lesson to learn the orbit of new comets accurately enough to determine if it is new here or has been around here before. It makes a difference, a multi-magnitude difference. Comet Austin. Discovered in 1989, it was expected to become a very bright comet in early 1990. It was found by Rodney Austin of New Zealand, his third visual discovery. When found, it was magnitude 11 and 2.4 times farther from the Sun than us. Perihelion, its closest point to the Sun, was to be April 9th, 1990, slightly within the orbit of Mercury, which is rather close. So here we have an intrinsically bright comet coming in very close to the Sun. What could go wrong? As it passed Mars' orbit, its rate of brightening began to decrease, and in the end, it was about 6 magnitudes or 100 times fainter than predicted. As Rodney Austin took this in stride, he later commented, "My comet out-Kohouteked Kohoutek." How about Comet Ison? It was expected to become a very bright comet in November 2013, but this one fizzled because it was too small to hold up under the high solar temperature of its short perihelion distance. We missed this one because we thought the nucleus was bigger than it was. The Sun simply fried this little comet. How about Comet 2019 Y4 Atlas, this year's early comet? It was a fluffy comet, and after it was discovered, it was determined that this is part of a family of comets, with another comet from this family visiting us about 180 years ago. So what do we know? We know coming in that this is a fragment of a larger comet, meaning it might have a greater than average tendency to break apart. I mean, the prior comet broke apart, forming this and other comets. And as Comet Atlas moved toward the Sun, it did break apart. We knew that it would come in close to the Sun, 4 times closer than we are. What we didn't know was how well it would survive when it got that hot. It did not survive. When some comets fragment, new material is exposed to the Sun, and they often outburst for a few days, exciting everyone as the comet temporarily becomes brighter. But when the dust clears, all that is left are a few fragments of comet nucleus, each of them subliming rather quickly. That brings us to Comet 2020 F8, Swan. Yeah, the pressure was put onto this comet after Comet Atlas failed. It did great early on, and yet it seems the comet nucleus may have broken within 3 weeks of discovery. This gave a slight outburst of brightness, raising hopes even more. But then over the next few weeks, it began to dim as the nuclear region, the bright spot in the Coma, faded. When I first picked it up on May 6, it did not seem to have that bright central condensation that comets usually have when they are having a healthy performance. Still, this comet swan put on a fantastic show in the Southern Hemisphere, seen against the dark morning sky. 4 more notes on this topic. Even when a comet performs well, things can still go sour. Let's talk about Halley's comet in 1986. It did well, but for many it did not live up to expectations, which were based upon the last time it was here in 1910. And it has a good reputation. Everyone learned about Halley's comet in school. Ever since then, it was the comet, the only comet that most people could recount by name. So when the general public thought of a bright comet, they thought of Halley. And those who saw a bright comet in 1910, well, there were 2 comets. The Great Comet of January 1910 was very bright and easily observed, and the other comet then was Halley's comet, not quite as bright. Some people who may recall seeing a bright comet in 1910 with the memory that it was Halley's actually saw the much brighter comet that year. Also in 1910, Halley's comet passed near the Earth. When Halley came back in 1986, it was not well placed in relation to the Earth, so we saw it from a much greater distance and it was fainter. Number 2, Northern versus Southern Hemisphere. I learned in the 1970s that generally comets discovered in the Northern Hemisphere went to perihelion, their closest point to the Sun, in the Southern Hemisphere, and vice versa. So they would be found in one hemisphere and put on a show in the other hemisphere. That's true sometimes, not always. Point is, some comets do become bright, but they do so in the hemisphere you do not live in. For instance, Halley's Comet 1986, very good for the Southern Hemisphere, not so well placed for the Northern Hemisphere. Comet enthusiasts, and this is kind of funny, banter back and forth, saying such things as, the Southern Hemisphere gets all the good comets, or they got the last one, the next one should be in my hemisphere. Comet humor. Number 3 is expectations. The press, and now the social media, can take a molehill and make it into a mountain. How many times has an astronomer said, such and such comet could become visible to the naked eye and be a really great object? And the next thing you know, it's being hyped as the comet of the decade, brighter than a full moon. Additionally, if you have 10 amateur and professional astronomers making predictions, the brightest one gets picked up and hyped and everyone else is ignored. Number 4 is light pollution. A comet looks much better in a dark sky than a light polluted sky, and you need to get dark adapted to see it well. Unless you do that, any comet would look less than spectacular, and it's not the comet's fault. Now back to the comets in our sky this week. Positions for the next 3 comets are found on my website, Podcast 22 Comet Positions. The 2 maps for these comets are Podcast 22 Map 1 for the Northern Hemisphere and Podcast 22 Map 2 for the Southern Hemisphere. We can still observe in the northern evening sky Comet 2017 T2 Pan-STARRS is floating through the Big Dipper this week and remains in the northern evening sky. It continues at magnitude 8.5. There's 2 more comets in the evening sky, but they're visible only from the Southern Hemisphere. They are Comet 2019 U6 Lemon and Comet 2020 F3 Neowise. They will both be moving north over the coming weeks. You have been listening to Looking Up with Don, podcast episode number 22 for June 3rd, 2020. Once again, the related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com. 2 H's. God willing and pod willing, I'll be back next week for another episode of Looking Up with Don. We will discuss what's going on in the night sky and discuss music that astronomers listen to while looking at the stars. Thank you for listening. See the sky this week. I'll see you next week.